One thing that's really important to understand when we're talking about electron and electron configurations and periodic trends is that electron configurations can help us understand the interplay between the nucleus and its valence electrons. And we're really only concerned with the valence electrons because the valence electrons are really what does the interaction between atoms. The core electrons don't interact. It's just like when I shake hands with you, my skin is touching your skin, my muscles and my tendons, even though they help mold my hand into the shape, aren't coming in contact with your muscles and your tendons. So it's the valence electron. So Z effective is really the interplay between the nucleus and its own valence electron. So there are three factors that have an impact on Z effective. So Z effective is force attractive minus force repulsive. So as the distance between the nucleus and the valence electrons increases, F attractive decreases, right? The electrons are getting farther away from the nucleus, and because it's a squared effect, the force of attraction will decrease exponentially. Similarly, as I have more layers of electrons between the valence electrons and the nucleus, the F repulsive also increases, and as a result, Z effective decreases. So as I go down the periodic table, I'm going to have a very large decrease in Z effective because my valence electrons are not only farther away from the nucleus, but there are this many more electrons between it and the nucleus. So one of the reasons why we use noble gas core is noble gas core tells us right away how many electrons are there as shielding electrons. So if I'm looking at potassium versus cesium, potassium has an electron configuration of argon, 4s1, and cesium has an electron configuration of xenon, 6s1. Argon has 18 electrons, xenon has 54 electrons. So not only is my distance higher, therefore I am much farther away from the attractive pull of the nucleus, I have a full 3 times the number of shielding electrons, repulsive force of electrons, between these valence electrons and its nucleus and these valence electrons and this nucleus. And remember, it's always the valence electrons and the nucleus. If I'm looking at the core electrons, the more protons I have, the more it's going to be strong. I don't care about that. So I have that two trends. If the distance and the shielding are the same, meaning they're in the same row, right? So all of these elements have the same shielding of krypton. All of their valence electrons are in the 5th energy level. So those two are the same. Then what starts to happen is that as I go across the periodic table, the number of protons increases. So I'm increasing that Q2 charge, and therefore my Z effective will increase because force attractive increases. Again, number 3 only comes into play when I'm talking about the same period. And that has to do with the number of protons. So this helps us understand, it's a vector quantity, right? Because forces are vector quantities. As I go up the periodic table, my Z effective increases, and that's because my F attractive increases because my distance is closer. My valence electrons are closer as I go up this way. And my F repulsive decreases because the number of core electrons, the shielding electrons, decreases. And my F attractive also increases this way because the number of protons increases. So these, again, are both vector quantities. I can then say that overall, francium is the weakest element as far as Z effective, and helium is the strongest. And it goes from bottom left to top right. So again, Z effective measures the strength of the nuclear attraction on the outermost electrons. And the overall trend is as you go up, and as you go from left to right, F attractive increases, Z effective increases, or as I go on a diagonal from the bottom left of the periodic table to the top right. So if I can compare. So I've already compared potassium and cesium. What happens if I compare strontium and carbon? Carbon will have a stronger Z effective because its valence electrons are only on the 2nd energy level. only have helium as their shielding, whereas strontium's electrons are on the fifth energy level away and have the shielding of krypton, or 36, 18 times the number of electrons. So you look at examples 1 and 2, reasons 1 and 2 first, and if those give you a clear winner, then you settle with that. However, if I'm looking at something like zinc versus titanium, zinc and titanium both have argon as their shielding electrons, and their valence electrons, 4s2, are the same distance away from the nucleus. But zinc has 8 more protons than titanium, so the Z effective of zinc will be slightly larger than the Z effective of titanium. This helps us understand why all the nonmetals are to the right of your periodic table. And it also helps understand why the Zintel boundary is actually at an angle and doesn't go straight down. Because nonmetals, we define nonmetals first and foremost by the fact that they make negatively charged ions. In order to create a negatively charged ion, it has to grab electrons away from someone. You have to have a strong nucleus in order to do that. Well, as I go down the periodic table, the strength of the nucleus on the ability to grab other people's electrons, much less keep your own, decreases. And so I'm going to have fewer and fewer atoms, elements within that row that are going to have that Z effective strong enough to grab electrons. Similarly, in a row, really the ones that have the highest Z effective are going to be the ones that are farthest to the right because they have the most number of protons within that. So farthest to the right will be the strongest, most likely to become negatively charged ions. Higher up on the periodic table, also stronger, more likely to become negatively charged electrons. This is why you have that fundamental difference where you have the Zintel boundary, that's at an angle that separates the strong nuclei from the weak nuclei. And this is why metals make up the large proportion of elements on the periodic table, because as I start to pack in more and more electrons, my nucleus's ability to hold on to those electrons becomes weaker and weaker, and therefore is more likely to become a positively charged ion in order to reach a stable state, which is the fundamental hallmark of what metals are.